Anil Kurmus, IBM Research at Zurich. Kernel exploitation and hardening, why we could have nice things. He'll be using split kernel.
Thank you very much. Good evening, everyone. It's a pleasure to be back at Balcom in the beautiful city that Novi Sad is, and also to see so many familiar faces once again. So in this talk, we're going to be talking about this split kernel project that we have, and essentially the motivation is the following. If you have some type of kernel hardening mechanism that you've developed, the first question that people will be asking you is, how much overhead does it have? Can we really use it in practice if it's 30% overhead? And essentially the motivation that we have here for this project is to say, even those cases where you have 30% overhead or 2x overhead, we might be able to make them actually very low overhead if we do things in the proper way. So essentially that's why we could have nice things even when people say that performance is a problem, right? So the talk is in two parts. First, we'll start with some background related to hardening, kernel vulnerabilities, and kernel hardening. And in the second part, I'll talk about the split kernel project itself. So, all right, let's start with a very simple program here, a program that takes two inputs, A and B, and computes A plus B squared, right? So if we wanted to harden this program, what would that mean? It would mean essentially after each computation asking some type of question like, are we doing okay with this computation? Are we doing okay actually with respect to the security properties that we want to guarantee to the memory safety and so on, right? And if we think more about it, asking the right, are we doing okay question has essentially four requirements. The first requirement is security requirements. We want this question to help us mitigate many likely vulnerabilities. So it can be that it degrades code execution vulnerability into a denial of service vulnerability, for instance, right? We want it to take as few resources as possible. We want performance to be good. So that means we don't want it to take too much memory, we don't want it to take too much CPU, we don't want it to take too much time. Next, we want also this mechanism to be easy to retrofit to many programs and have an easy configuration in practice. So something that we can use across many programs, right? Without having to spend too much manual time into making the program work. And finally, last but not least, we want this to not break the program. We want correctness to be ensured in order. So if just asking those questions, if the implementation of the program breaks the program or gives the wrong result for our A plus B program example, then we've completely messed up things, right? So that's a very important point. All right, so some examples of hardening features. You might have heard of SSP, heap hardening, format string hardening. SSP is stack special protection, also known as stack cookies. And earlier this morning, you've had a very good introduction on control flow integrity, code pointer integrity, safe stack, and there are also other mechanisms in academia and to come into production code on basic hardened features that will help improve security. But the important thing, without going into the details of these techniques, is that although all of these techniques mitigate some vulnerabilities, they all have some performance overhead. So the question that people will ask is hardening worth it, right? So answering that question is pretty difficult. So let's try with some easy to answer cases. For instance, let's take a wall clock. Who thinks here that in the case of a wall clock that we would need ASLR? All right, there are a few courageous people, but otherwise mostly reasonable people here that don't think that we need ASLR on a wall clock. But we have to be careful because there have been many cases where we would think that there's no security implication of the thing that we're seeing, such as this is the Great Seal bug. So this was offered by the Russians in 1945 to the American embassy in Moscow. So it looks like an American seal made as a wood carving, but inside there's this essentially antenna with a resonant cavity that allows you to eavesdrop on every conversation that's happening inside the room, right? So sometimes it can be tricky, and the question is, is that relevant to this day? And I think the corresponding analogy nowadays would be the Internet of Things, so an IoT wall clock. Inside your home, you have, for instance, this IoT wall clock, which has actually a camera and also Wi-Fi connectivity. So suddenly it becomes interesting, right? But okay, I digress. Let's recap. We have cases that require hardening and cases that don't, but it's hard to tell really at the development phase. It would be better if we can configure that during the deployment of the system. Meaning, if I'm a kernel developer, it's really not the best place to decide on what basically security policies people will be implementing later on, right? And we also said that it's often a security versus performance trade-off, right? All right. So let's go back to the kernel vulnerabilities and have a little bit of introduction around it. So it's actually a long-standing issue. I think the best report around it is the 1972 report from the US Air Force. It's also known as the Anderson report. In particular, it contains an appendix which has a list of classes of vulnerabilities which are still relevant to this day, things like kernel info leaks, for instance. And I've also put a few examples there of examples of vulnerability of today, where you could, if you're interested, you could go ahead and have a look at their description. So for instance, the Duku exploit uses Windows kernel true type font parsing. So vulnerability. So for some reason, the Windows kernel is parsing TTF fonts inside the kernel, right, in kernel mode. And that was what Duku used as a privilege escalation mechanisms. iOS jailbreaks are very often using kernel exploits. So very recently, there was the biggest exploit, which is used after free vulnerability. And also very interesting in Linux's case is the Sctp vulnerability, the remote kernel exploit based on the network protocol. So that you can find in FRAC, and also there's a book called Attacking the Core, which is excellent. And there are many, many more examples if you're interested in that area. But we'll give one example of a particular class of kernel vulnerability called stack info leak due to uninitialized data on the kernel stack. So on the left, we have the stack frame of a function A, all right? And this function A has some sensitive data, say cryptographic keys, right? And then we have this function B, which is described in the middle here, which uses a struct, which declares a struct on the stack, and it's only half initializing it. It's not initializing the member B, right? And then copies that back to the user without initializing it, meaning that the content there will correspond to previous code that was there on the stack. And if function A executed right before it ends at the right location, then we're leaking the sensitive data to user space, right? So that's, I think, a class of vulnerability that's very easy to understand and also can be quite easy to exploit, yeah. So what can we do with this? What type of hardening mechanisms can we apply here that would mitigate those vulnerabilities? So you can essentially use kernel stack clearance techniques, meaning we just zero the kernel stack opportunistically when we want in order to make sure that there's no uninitialized data remaining. So in the case of GR security, there's the stack leak option, which for instance will zero this kernel stack at the end of each kernel syscall, right? So that's already very expensive actually as a mitigation mechanism, and does not prevent all the vulnerabilities of this type. So better would be zeroing after each stack allocation. The reason is that in the previous example that I gave, when function B is called, I didn't even return from the syscall yet, so I can still leak the data, and I will leak the data. But if we zero at each stack allocation, then we're not leaking that data. So it's even more expensive, but at least it's mitigating even more vulnerabilities. So it's actually quite interesting for our split kernel use case here. And that's why I'm asking here, do we always have to pay this quest? And I'm going to give an example with OpenSSH now. So the OpenSSH daemon, as you might know, is privilege separated. There's a paper by Nils Povo et al. At Using Security in 2003. So the main daemon essentially runs as root, but there's a sandbox component, so a separate process which is running as a separate user ID, SSHD UID, which is essentially then unprivileged, right? So let's go through the scenarios. If I'm an attacker and I gain code execution in the sandbox process, right, I could escape via a kernel exploit. If I have a good kernel exploit, then I get out of the sandbox and basically I use a local privilege escalation vulnerability. And there, kernel hardening would be very, very beneficial in that case, right? But if I'm an attacker and I gain code execution directly in the main process, which is running as root, I already have full access to the system. So there's no point that I use a privilege escalation vulnerability. I'm already full root. So in this case, kernel hardening will just cause unnecessary overhead. So we just want to get rid of kernel hardening in for that specific process, but not for the other process, right? So that's where our approach comes in. And what if we could get and select kernel hardening at runtime at no cost and in a granular way? So for instance, at process granularity, right? So this is a paper that we did together with Robbie Zippel, who was an excellent student that worked with me at IBM. And the paper, you can also have a look at, I put the link also in the description of the talk. So a bit of an overview of the approach there. So on the left-hand side, we have here what we call split-based code. So code that is actually very close to the actual code that the kernel will be normally built with. And on the right-hand side, we have split hardened code. So that's code with added instrumentation and hardening checks, right? And they share the same data. So they're using the same data. So it's essentially one kernel in the sense that it's one trust domain, right? But we have two modes of execution, right? And at runtime, so for instance, at system call entry, for some processes, we can say, I'm going to use the split-based mode. For some other processes, I can say I'm going to use split-hardened mode. And similarly, for interrupt handlers, for instance, I can say, okay, this is interrupt from the disk. I'm going to use base mode because I'm trusting my disk. But for the network interface, which is connected to the internet, I'm going to use hardened mode because I'm not trusting that network interface. But for the network interface that goes to my DB, I'm trusting that interface in the sense that it's very unlikely that I will have remote kernel exploits coming from there. So then I put it in base mode because performance is very important. So essentially, we have two modes and one kernel. All right. The point is, as I said, it's one single trust domain, meaning if I compromise any of the two modes, I really compromise the entire kernel. There's no isolation between both, right? But the kernel is much less likely to be compromised when we run in the hardened mode, right? So we had 4 design goals when starting this project. The first one is to have no split-based overhead, meaning we want, when we run in split-based mode, which is basically the legacy normal performant mode, we want everything to run as fast as possible and actually just as fast as a normal system. This means that the split-based code will need to be changed as little as possible. It needs to stay exactly the same. The second design goal is no control flow from split hardened to split base. So this means that once we enter split hardened code, we don't want to accidentally go back into split base code. And I'll get back to that in an example I am going to give in the next slides. The third goal is to have some runtime configurability. As I said, we can say this process needs to be run in hardened mode, this other one needs to be run in base mode. So I need a way of configuring that. I might want to say all these user IDs should always run in base mode, these other ones can run in hardened mode. Same thing with interrupts and so on. So we have also that. And finally, we wanted some level of maintainability in the sense that we wanted to limit the changes to the Linux kernel in order to make it easy to integrate such an approach in the future. All right, so I'm going to go through an example with OpenSSH and split kernel. So we have our privilege-separated SSH daemon. We have SSH running as root and SSH running as user SSHD, which is the sandbox SSHD process, right? and it's going to do some system call. This system call is going to go into split base code. It will do some things, and eventually it will return. And the goal is that when we do the system call, we have no overhead over a base system, as we said earlier. So let's go through a read system call first. So I do a read system call, and at the system call entry, there will be a compare branch. So this is the only addition that we have to the system call. There will just be one check to see whether the current process needs to run in base mode or in hardened mode. Once we decide that it's in base mode, everything else actually remains the same. So in this case, we have a function called sysread that will call another function called doRead. And doRead, just to make things a little bit interesting here, is actually making an indirect call to the function VFS_read. So the register array X is taking the value of VFS_read, and then we're jumping into VFS_read, right? All right. So this means that we'll have low overhead by design because we basically did not change anything to the way the system call normally operates. We didn't really add any code, right? In split hardened mode, it gets more interesting. So first, I'll give a little bit. I'll show how we actually do this. For instance, during boot scripts, you could add the UID of SSHD into a list of UIDs that need to be run into hardened mode. So whenever the kernel detects basically a set UID to this UID, it will be put into hardened mode, right? And this means that we don't need to change anything about the way SSHD currently works. We can just use it as it is, and this will work perfectly fine. All right. So let's continue for our example here. So we run SSHD, it will do some system call, and the goal here is really the important thing, is to remain in the hardened mode. So we don't want accidentally to go into the split base code. So in order to do that, the idea is that we'll instrument, one idea would be to instrument every base function, right? But if we do that, this will create a lot of overhead in split base mode. Yeah. The idea meaning if we detect that a split base code is running, although it should be running in hardened mode, then we just send you back essentially to hardened mode. So meaning it's better to instrument actually at the call source. Because at the call source, we can add overhead in the split hardened code, right? So the way we do this is by modifying or instrumenting split hardened function calls. So in the case of direct calls, we just modify them at build time, as I've shown, as I will show in a minute. And for indirect calls, we use something called alternative function addresses, and there's a bit of implementation of the indirect calls. So right, so first I make a recall within the hardened process context, right? So this will go and call doRead HDN, which is the hardened version of the doRead function, which has been produced by our compiler. And in doRead HDN, so this is where things get interesting, because we said that there's a function pointer that we're using, meaning from the shared data section, which is the same as the split base code. So the value needs to be exactly the same. It needs to be the VFS_read address. But instead of directly jumping to the VFS_read address, what we do is we first dereference what's at the address of VFS_read -8. Because at that address, we've put the address actually of the hardened version of VFS_read. So meaning what happens is that we will remain in hardened mode with efficient indirect call instrumentation. So this will have super low overhead. All right, maybe you're wondering, how do we build the kernel? So those would go split builds. For a given translation unit, first we have the first step here, which is compiler, and we produce assembly. And our technique is basically based on an assembly pass. So we have an assembly preprocessor, which is going to introduce not only the hardening mechanism, but also the little tricks that I mentioned, for instance, in order to make sure that we have the alternative function addresses and so on, right? So then we call the assembler as we normally would. Then there's an additional trick when we have the two objects and we want to merge them into one split object, right? because we have the hardened version of the code that was compiled and also the base version, but they all have their own data sections, right? So we want the linker to merge them. And what we do is we use actually symbol weakening, ELF symbol weakening, to ensure that these two symbols will be merged when we link things. All right. So another implementation highlighted that we've implemented 3 different features. We've implemented kernel stack exhaustion prevention, which means that each time the kernel stack pointer is decremented, we check whether we are going to run out of kernel stack space. Because if we do, this is a way of essentially corrupting important kernel data structures on Linux, and that will give you basically automatic local privilege escalation, right? Another mitigation mechanism we implemented is stack clearance, and lastly, we also implemented function pointer protection, mostly for the sake of the arguments of what would happen if we had something like control for integrity. The important thing about these kernel hardening mechanisms is that we don't really implement new kernel hardening mechanisms. We just want to show that if you have a kernel hardening mechanism, we can use them with split kernel, right? Next, we've also implemented code segregation. So in order to make sure that our split-based code runs as fast as possible and that we don't have any performance problems due to special locality, so cache misses on the code, we just put all the hardened code separately. We've also done a port for x86, but also MIPS32. It runs on a little router. And we also have full loadable kernel module support, meaning you can use your Linux kernel as you usually would. All the Linux kernel modules are working with the system. All right, a little bit more about the implementation. I'm not going to go through the details here, but essentially for the build system, we had just about 600 lines of code. So that's actually a fairly reasonable amount of change. For the kernel modifications, meaning that's mostly things related to bindings, right? How we configure users to be used in hardened mode and so on. That was just about 500 lines of code. And the hardened mechanism themselves, so basically the preprocessor stuff, was about 800 lines of code. And you would need more if you want to add more hardening mechanisms and so on, right? So meaning the implementation is actually fairly manageable. All right, so I think it's time for a little bit of a demo to show how things work. So should have here. All right. So we have a little bit a kernel module which we call SOS here, which is essentially a damn vulnerable kernel module, which is all the vulnerabilities you can imagine. And I'm just going to explain one vulnerability that's in there. So this kernel module implements a procoffice interface. So there's basically a file we can read from. And when we read from this file, it will essentially copy the contents of an uninitialized buffer here. There's a 128-byte buffer in it, which is essentially copied back into the user buffer. So that's obviously leaking kernel stack information. The interesting thing here is before leaking in this function where we do the write, we also call this other function called secret stack. And the function secret stack has, well, for instance, a secret cryptographic key, right? So let's see how this works in practice. So if we do, let's maybe just look at the strings there. We see that directly the secret password as we had expected, right? Because it's just leaking the kernel stack. So we could look at the dump and we have 128 bytes and so on. So because we have a split virtual machine here, we've run the split kernel. Now we want to show what would happen if we run in hardened mode. So this is, we're running as root here, right? And we can show that we are running in base mode. So when this file returns 0, it means that we're running in base mode. If it returns 1, it means that we're running in hardened mode. So let's switch to user split, which is actually a hardened mode user. We can check now that we're running in hardened mode. And the reason for that is that there's a file that specifies, as I mentioned before, that user ID 1000, so user ID split, will be run in hardened mode. Right. Okay. So if we go into split, and if we try to cat proc SOS this time, we're hoping not to see anything because our hardening mechanism should kick in, right? So that's exactly what we see. So if we look at the dump here, we only have 128 bytes worth of zeros because it was all initialized by our split mode hardening. So I'll just show the disassembly to show exactly what we have here. So this is the normal uninitialized write function, which is, interestingly enough, so GCC unrolled that, the memcopy, and it's essentially copying byte by byte the contents of the stack there. So let's look at the hardened version of it in the disassembly. Yeah, so it's this one. And here there's actually a lot of different hardening mechanisms that come into play, which is why this function is so big. But if we scroll down enough, we should see. So here there is repeated store just after at 22F, location 2TF, which is essentially clearing out the kernel stack. So that happens before all the copying goes on. So that's why we're only seeing zeros and it's hardened, right? All right. So I think that's it for the demo. We can now talk a little bit about performance. And usually performance is very boring, but in this particular project, it's all about performance, and it's actually quite interesting, the results that we have. So first, some micro benchmarks. We're just looking at the overhead that we have over a normal Linux kernel. So this is a normalized execution time, meaning if we are at 1, for instance, in split base mode, we're about 1, which means that we're running just as fast as a normal Linux kernel. So that's very good. And also the other interesting thing here is that when the hardening is turned on, either at runtime or either if we use a fully hardened system, meaning if we have a system without any of split kernel but applying the exact same hardening mechanisms, we're running pretty much with the same overhead. So that's also very good. Some micro benchmarks. We talk about the OpenSSH use case. Inside the paper, there are more benchmarks if you're interested. So we do 2 benchmarks with OpenSSH. One is file transfer. So we just transfer a big file and we look at how much time it takes. And the second one is we look at the login and logout time, how it is affected in the different settings. So we have one case which is split base, as I mentioned before. That means that we're running split kernel but in base mode. There's the split hardened case. It has two different modes that I will explain later on. And the fully hardened case, which is without split kernel, but we're putting all of the hardening mechanisms. So the first benchmark, mainly the thing that we can say is that everything is below 5% overhead. And the reason is that it's a benchmark that is not really kernel intensive, right? It's mostly file transfer, so we're network bound. So this is still very interesting because it means that split kernel, for instance, we could use it to opportunistically harden some workloads, right? Because performance doesn't really matter in that case, we can opt to turn it on, right? To turn on hardening and not think about the security implications or whether we need it really or not. But that's not something that we have if we have a fully hardened system, because I would have to recompile the kernel, and that's usually not something that's manageable in production systems. All right, so in the other benchmark that we have, we can see that whether we run in split base mode or in split hardened mode binding 1, we have no overhead over the normal system. So binding one is essentially when we say SSHD is running into hardened mode, right? But the network interface where SSH communication is coming from is not put into hardened mode. In binding 2, we put both of them, right? So when we only look at binding 1, so just the SSH daemon, we have basically no overhead or almost no overhead. And the reason for that is that actually the sandbox section of SSH is only doing about 1,000 system calls versus about 100,000 system calls on the main SSH daemon, right? Plus the network traffic and so on. So that's why if we add hardening there, it's both very good in terms of security and it doesn't cost us anything. So that's a great trade-off that we can have thanks to a split kernel. But when we enable binding 2, we can see that we have an overhead that's close to 30%, which is also the overhead that we have with the fully hardened kernel. And the question that you might have is, should I pick binding 1 or binding 2 if I have such a system? And that depends on how much you value the performance there or the security. So yeah, I think it's good that it's configurable because then people can, or distributors can decide on their own, right? All right. So I'm going to conclude here. So what can we use split kernel for? As we said, if I'm a sysadmin, a developer, or a packager, it's very nice because I can pick and tailor the kernel to the security and performance needs that I have, right? So that's an obvious use case. But if I'm also a kernel maintainer, there's all these debates on whether we should be including this hardening patch or not. We don't need to do that anymore. We just basically include everything during the build process, but people decide at runtime because it doesn't cost anything to include all these hardening features in terms of performance, right? So, and finally, if you're a researcher, for instance, if you're a PhD student and you have a paper and people keep rejecting it because there's too much performance overhead, you can argue that together with split kernel, it doesn't really matter because you can have cases, you can use it in cases where the performance is not going to matter, where you will have very low performance overhead anyway. All right. So to conclude, essentially we could have nice things, and with that, I'll be open for your questions. Questions? Go ahead.
So it's an interesting trade-off. So you're not protecting a part of the applications where you think that you have low potential attack surface, and you're protecting the applications that have potentially high attack surface. Now, what I'm wondering is the kernel is such a big beast of code. How do you know that even in the protected version there's not anything bad happening if you're just relying on these existing techniques? So that an attacker can bypass all the defenses that you have there. You're not enforcing full memory safety, you're not enforcing full type safety. So there's a lot of bad stuff that can happen, even if you do use the different hardening techniques.
So in the case of actually, so we didn't go much into the hardening techniques themselves, but in theory, there's nothing that would prevent you to have full memory safety in the hardened mode, right?
Do you know of any full memory safety technique that has been implemented for the kernel?
For the kernel, no, but you could use something like self-bound CTS, for instance, and it's not really perfect, but for instance, you could have something like that, right? And the point is, the overhead, you're not going to be paying it in the other modes. And it's not about attack surface, actually. So I think it's very important. So it's more about something that's running as root. If it's compromised, we don't care about protecting the kernel from it because it's already root, it's already over, right? So that's part of the mitigation. So on the other hand, I agree that the 3 hardening mechanisms that we presented here are not something that will protect against all possible vulnerabilities, right? I don't think anybody would think about claiming that, but so they will be of course, vulnerabilities that you can still exploit together with those 3 hardening mechanisms. However, if you have, for instance, a stack-based info leak, such as the one that I showed, which is a very trivial one, it's actually fully prevented with that hardening, because there's no way of exploiting it, right? So there will be definitely cases where you can say it's really fully protected in that case. So, yeah, I think, yeah.
Okay, so if I understood well, you actually have certain functions in the kernel, or functions compiled twice. So how much larger is the kernel?
Right. So I don't have the numbers exactly here, but they are in the paper. The thing to keep in mind is that only the code section doubles in size, and the kernel is actually a few megabytes, right? So in terms of code size of the kernel, if it's 3 megabytes or 6 megabytes, it's typically not a huge difference. Even at runtime, if you consider the fact that it's going to be in RAM and so on, so it's going to take some RAM. If you have 3 megabytes versus 6 megabytes in RAM, nowadays it doesn't really matter.
Well, yeah, on desktops and laptops, but you also made it for MIPS 32, for routers.
So the good thing about MIPS 32 is that the kernel is then, people configure the kernel to be much smaller.
Yeah.
So I don't have the numbers, it's in the paper, but then also the doubling is also much less impressive as well. And they have, like, I think, I don't know exactly, I would have to check the paper, but there's maybe 128 megabytes of RAM or 256 megabytes of RAM already, and you have maybe a 500 kilobyte kernel. So it's not really a huge deal. It is that it's a difference, but there's an impact from. Yeah.
I'm not really into kernel, but I know that kernel is usually compiled with OS optimization. So for size, it's important to avoid cache misses.
Exactly. Yeah.
So I thought that bigger kernel would impact performance in some way.
Right. So that's where I mentioned it very quickly in one slide. So we have something called code segregation, meaning that all of the hardened code, we put it separately. Meaning if you're only going to be running the system in base mode, you're not going to have any more cache misses than on your normal system. Because all of the other code is actually in a separate location, which is not going to impact spatial locality. So we've kind of considered that angle.
Yeah, I was having in mind basically when you're alternating between modes, that would impact.
Then definitely, but on the other hand, then you still have the benefit of having a system which is not always running in hardened mode and paying always the performance overhead, which would typically be higher, right? For instance, for the 3 hardening mechanisms that I showed, it's clearly high. So, of course, when you start using the hardening, you will pay some performance overhead.
Okay, thank you.
Thank you.
Hi.
Hey.
In terms of ease of applying this or performance-wise, how does it compare to, I don't know, something like GR security kernel patches?
So,
is it even comparable?
So I wouldn't compare it because ours is a research project and GR security has been around for a long time and they've been supporting. Oh, you can't hear? So I wouldn't compare it because, so the question is, can you compare it to GR security? And so this is a research project and GR security has been around for a long time and the good thing about it is that they're really supporting and they have all these patches and so they need to put a lot of hard work into basically having their hardening patches apply to essentially the latest version of the Linux kernel. So that's not something that, at least for now, we're willing to do. So from that perspective, it doesn't really compare. But it also, from a much more theoretical perspective, what we want to do is not kernel hardening, because that's already been done and your security is actually very good at it. What we want to do is making it less of a problem of doing kernel hardening, right? So it's something that could be used potentially with hardening mechanisms like your security, but the drawback is that you need to think about the hardening mechanisms together with split kernel. So they will need to be essentially rewritten. Yeah, you can't just pick a hardening mechanism and say, I want to enable it and it's going to work directly with split kernel.
It's not a push button solution.
Yeah.